let's spend a couple minutes talking about forces. A force is just a push or a pull that one object exerts on another. There's only ever two objects involved at a time, not three, not four. The two broad categories of forces are contact forces, which are kind of your everyday forces like a hand pushing on the table, a normal force from a table pushing on a book, a tension force from a string pulling on a wagon. Anything like that is going to be a contact force. The two objects have to be touching in order for those to happen. There are also field forces, which go along with kind of the fundamental forces of the universe. Gravity is obviously the big one that we use most often, but we'll also talk about the electric force and the magnetic force a little bit. When we talk about forces, we always talk about Newton's three laws of motion. So the first law, the law of inertia, says that an object in motion will stay in motion, an object at rest will stay at rest until acted upon by a net external force. Pretty much if you don't mess with something, then the velocity of an object won't change. Newton's second law has to do with the proportionality of acceleration with relation to the net force and the mass. And then Newton's third law, probably the most misunderstood. For every action, there's an equal and opposite reaction. This always needs to follow the format: if object A pushes on object B, then object B pushes on object A. There can't be any third objects in the mix. It's always between just two objects. We are going to start off by talking about Newton's first law, because that's kind of the easiest one. The case where the object is in equilibrium, the forces on it are balanced. So we've got three forces acting on an object moving with a constant velocity. Nudge, nudge, wink, wink. Constant velocity means that the acceleration is zero, right? Which means the forces have to be balanced. So here we've got force 1 and force 2 written in IJK notation, which, if you recall, it's the three-dimensional way of writing forces. I corresponds to the x direction, J corresponds to the y direction, and K corresponds to the z direction. So I've got two of the forces, and I know that, well, if this object is moving with a constant velocity, then force 3 has to cancel out the first two forces. So just simple math, how do I get to 0? You get negative 5i hat plus 8j hat plus 7k hat. Woo. Another pretty simple problem, a book sits on a table. If we wanted to draw a free body diagram for it, we'd have the weight going down, we'd have the normal force going up. We write our net force equation, net force equals 0. Normal force minus weight is equal to 0. Normal force is equal to the weight because it's a third law pair. No, wrong. It is not a third law pair. You fell for it, okay? If you think very carefully about the objects causing the normal force, the objects causing the gravitational force on the book, okay, the normal force is caused by the table pushing upward on the book. The gravitational force is caused by the earth pulling downward on the book. Whoa, whoa, whoa. There's three objects involved there: the table, the book, and the earth. This is not a third law pair. Don't be fooled, okay? The normal force and the weight are equal because the book is at rest, not because it is a third law pair. Let's look at another more complicated equilibrium problem. This is called the hanging lamp problem. I don't know why they call it that. I guess there's a lot of hanging lamps. So here we've got a lantern suspended by two strings, each with different angles with respect to the ceiling. Just like with kinematics and projectiles, you can't mix your X stuff and your Y stuff, your horizontal stuff and your vertical stuff. Each axis has to be evaluated independently. So we've got to split those tension vectors into components, which I've done so there. And since this lantern is just suspended, its acceleration is 0 in both the X direction and the Y direction. So here I am setting up the Y direction. It's equal to 0. The two upward components of the tension must equal the downward tension that's equal to the weight. So I can almost solve it, almost. But here I've got T2 times the square root of 3 plus T3 is equal to 852. That's as simple as I could get it with the vertical equation alone. Okay, at this point, I take a break. I look at the horizontal direction, because in the horizontal direction, my forces have to balance as well. I do the net force equation for that, and I solve it. And here I can actually solve it all the way down to T2 is equal to T3 times the square root of 3. I'm going to take that, and I'm going to pop it into my vertical equation. All right. So some stuff cancels out, and I can solve, actually, T3 for a value of 213 newtons. Okay, so that is the total tension in T3. Then I can take this T3 tension and pop it back in to the equation for T2. It's kind of lame. You just multiply it by the square root of 3 to find what the tension in T2 is. So that's the process when you have a couple of different angles. When you actually start getting stuff moving, things get a little more exciting, but the problem-solving process remains the same. You'll want to draw a free body diagram, but now you want to pay attention. Well, is this object accelerating? If so, I want to pay close attention to the direction of the acceleration. And mathematically, when you write your net force equation, you'll always want to write it so that the acceleration is positive, because I guarantee that you will forget to make the acceleration negative. So just make it positive, define all of your forces in terms of the direction of the acceleration. Is it matching the direction of the acceleration, or is it mismatching? And so kind of one of the classic starter Newton's second law problems is talking about a person in an elevator. So at first, the elevator is accelerating upwards, then the elevator travels at a constant speed, then the elevator is going to slow down as it reaches the top floor. And so while we're in the elevator, we want to know the person's apparent weight. And just a refresher, apparent weight is the normal force. You don't really sense the earth pulling on you unless you are in contact with something that's giving you like a perspective, like a frame of reference. All right, that's why like when you're skydiving, it's not like gravity isn't pulling on you, because that's why you're falling, literally. But your body is kind of freaked out because it doesn't have a normal force to orient itself to give an apparent weight. So when we're asking for apparent weight, we are asking for the normal force. So if we are accelerating upwards, all right, well, that means we have to have a net force in the upward direction. There's only two forces acting here, right? The normal force and the weight. That must mean the normal force is bigger than the weight in order to have that upwards acceleration. So writing your net force equation, plugging in your forces, rearranging and solving. I didn't plug in numbers because I think it's more intuitive to leave it in this form right here. My normal force is equal to mass times, parentheses, the acceleration due to gravity plus the acceleration in the elevator. Okay, when you're plugging in these numbers, plug in everything as positive. Don't plug in like negative 9.8 or negative 10. Okay, literally this normal force, this apparent weight, should be larger because the acceleration is upwards. It's making you feel extra heavy. Okay, for the next part, if you're moving at a constant velocity, did you fall for my trap? If it's a constant velocity, the acceleration should be 0, which means the forces are balanced and normal force is just equal to the weight. That is normal, pun intended. Okay. As we reach the top floor, we are slowing down, and here it might be useful to kind of think, whoa, okay, slowing down, that's like a deceleration. I know Miss Rittenhouse hates that word. What does it mean? Okay, if you're slowing down, that means the sign on your acceleration must be opposite the sign on your velocity. So if we were going up, but we're slowing down, that means our acceleration has to be downward. And I don't know if you noticed, but Fg, the weight, is staying the same in these trials. Your person is not eating a Big Mac, or I don't even want to think about how he could possibly be losing body mass, but the weight is the same each and every time. It's just the apparent weight that is changing. So in order to have a downward acceleration, the normal force must be less than the weight. And remember, okay, you're going to forget to plug in a negative sign for your acceleration. So you might as well just define the acceleration direction to be positive. Okay, so if down is positive, then Fg is going to be positive and Fn is going to be negative in this case. So setting up your net force equation, you get that the normal force is equal to m times parentheses g minus a. This makes sense, right? Because g is roughly 10, and our acceleration, it says, is 2. We're always trying to get positive numbers for our forces just because that's easier to imagine. Okay, so that is a super brief summary on how to work with force problems.